All right, so on Monday, we had looked at this set of data. And where we were looking at the population of women under the age of 18 from year 2020 projected through 2060. And we had put that aligned data in our calculator, and we aligned the year, which is typically what we do. And I probably should share my screen or the recording is not going to see it. Let's share the screen. That's better. And we then graphed the scatter plot based on that aligned data. And the scatter plot looked fairly linear, looked pretty linear. We had a couple of points that deviated from a perfectly straight line. And then we graphed a line that they told us to graph. We graphed y equals 0.1 x plus 36. And we saw that that particular line didn't fit our scatter plot very well. So then we actually took 2 points off the scatter plot. We picked 2 points and we used the 2 points and the point slope equation to find an equation of the line that fit our data a little bit better. And then we graphed that. And that line was based on the 2 points, 25, 38.2 and 60, 43.6, which are actual points in our data set. And I said, wouldn't it be nice if we had a much easier way of calculating the line that fits our data the best, instead of having to pick 2 points? I mean, honestly, picking 2 points, finding the slope, plugging that into the point slope equation is a lot of calculation and it's fairly tedious. And it can lots of places to make mistakes. So what if your calculator can do this for you? So can it take your data and find the line that fits your data the best? And the answer is, why, yes, it can. So if I go to my calculator, if my mouse will cooperate, if I go to my calculator and I go to my stat menu and I go over to my calculate menu, number 4 says ln reg ax plus b. And that is a linear regression where they're going to give you the slope, which is the variable a, and they're going to give you the y-intercept, which is the variable b. So you're going to run what's called a linear regression on your data, and it's going to give you the slope of your line and the y-intercept, and you can graph that. Okay, so let me show you how to do that. So we have number 4, and it asks you, first thing, what data are we trying to find the equation of the line for? And I had put my data in L1 and L2. And I think most of you had also. So I'm good. My X's, my aligned years, was in L1. And then my number of women under the age of 18 was in L2. I don't have a frequency list. Now you'll notice down here, I have store reg equation. So I can actually take that equation that my calculator calculates for me and store it in my y equals. And this is the most tedious part of this, because you got to go find the variable to store that equation in. Okay, so here we go. You ready? Below the down arrow, you've got the clear, and right next to the clear, you've got a menu that says VARS. That's your variables menu. So we're going to click on that. And look at number, well, let's go. Look at the second item over in the menu, the Y variables. That is that Y1, Y2, Y3, 4, etc. So we go there. So variables, Y variables. And then we are in the class that's called functions and modeling. So we're going to go to functions and we're going to click or highlight and select Y1. Actually, I'm going to put it in like Y3 because I think I got Y1 and Y2 filled up. So let's try it in Y3. I'm putting it in Y3 because I put those two equations in Y1 and Y2 the other day. So I'm going to put it in Y3. Really doesn't matter. Okay. And then I'm going to calculate it. So I'm going to go down, highlight, calculate, and hit enter. So the equation that fits my data the best is y equals 0.155x plus 34.2, the 7 repeats. So the first number they give you, the A, is the slope of that line. The second number they give you is the y-intercept of that line. Now, do you see r squared and r on your calculator?
No.
No, okay, we'll turn that on in just a second. This is a measure of how accurate that line is. 0.997, that is a line. That data fits that line almost perfectly. Okay? We'll talk about how you turn that on in just a second. All right, so now I'm going to go look at my graph because I have my scatter plot in. I graphed the original line they gave me. I graphed the line that I found from the 2 points. And now I have in my y equals the regression line. Let's make sure that's true. Okay, so there is the line that they originally gave me. There is the line that we found based on the 2 points. And there's the regression line. So if I hit the graph button, there's the original, there's the one we found, there's the regression line. So the regression line is very close to what I found using the 2 points because the data was fairly linear. And so I got a pretty good approximation just taking 2 points and finding the equation of the line. So given a set of data, you can find the line that fits your data the best, and you can store it in your y equals and then graph it. All right, so let's do this for another example. So here are your steps. Enter the data into list of your graphing utility, your calculator. The first thing you want to do is create the scatter plot, and you want to do that first because if it's not linear, then you're not going to move forward. If your data is just random, then why try to find a line that fits it? Use the graphing utility to obtain the linear equation that is the best fit. You do that by going stat calc number 4. Tell your calculator where you put your data, what lists, and then you can calculate the regression. Graph the linear function unrounded and the data points on the same graph to see how well the function fits the data. Report the function and/or numerical results in a way that makes sense in the context of the problem, with appropriate units and with the variables identified. My phone is blowing up. Unless otherwise indicated, report functions with coefficients rounded to 3 decimal places. My sister's in the hospital, so maybe I should check this. My oldest sister is in the hospital. Something going on there. All right. We're going to put this data in our calculator. the total US population for selected years beginning in 1960 and projected to 2050 is shown below, with the population given in millions. So we are going to align this data, and typically what we align is the year. Obviously, we're probably not going to align the Y values, the population, but we are going to align the year. Align the data to represent the number of years after 1960 and draw a scatter plot. Create the linear equation that best fit for this data, that is the best fit for this data, where Y is in millions and X is the number of years after 1960. Then graph the equation of the linear model on the same graph with the scatter plot, and then discuss how well it fits. And then we're going to align the data differently. And this is, once you have your data in your calculator, aligning the data to some other value is so easy to do. You do not have to re-enter all the X values. And then we're going to see how that changes the model. It doesn't. And then we'll use unrounded models to estimate the population in the year 2000 and 2010. Okay, so we're going to first align this data so that the first list is going to be the years after 1960. So since we start at 1960, the number of years after 1960 is 0. So 1960 minus 1960 is 0. And then you take each one of those years and you subtract 1960. So this would be 5, correct? 10, 15, 20, 25, 30, and then it gets weird over here. 35, and then it's all of a sudden it's 38. 1998 minus 1960, is that 38? And then it's 40. And then what is it? Is it 43? And then all of a sudden it jumps 22 years. What happened to the 22 years? I don't know. So what is that? 60, 40, is that 65? And is that 40, 10, is that 90? Okay, so I want you to put in one list the align year, 0, 5, 10, 15, etc. And then in another list, I want you to put the population in millions. I'll give you a minute to do that. Arrow up till you highlight the list and then hit the clear button.
Like the Y and the X and hit clear.
No, you're going to go to your lists. So you're going to go out of here. You're going to go stat, edit. Now you're in your list.
Oh,
Oh, no, where were you? You were in a table, weren't
I
you?
don't know.
So stat, edit is where you're going. You're going to go to your lists. What you puzzling over?
And on the list too, do we put the population?
Yes, the second list, L2. Now, my data is in L3 and L4 because I just used L1 and L2 for the previous example. So wherever you put your data, it's fine. But mine is going to be in a different list. You wanna borrow? Since everybody's here that's gonna be here, I'm gonna shut and lock the door. We had a stranger on campus yesterday.
Oh.
Well, the door safe and lock the door shut. How are we doing? Is everybody going in?
No, yeah, we're getting there.
And I am gonna take my time with this because it is something we do over and over and over. Oh, sorry. Yes, that. Dang dongle. I somewhat wonder that if they left out the years from 2003 to 2025 because they didn't fit a linear model. That would, because this is actual data, US Census data. This is actual data. And by the way, there are so many places you can find real data. My daughter-in-law sent me, she's always sends me things, tell this to your statistics class. And one of the things she sent me a couple of weeks ago was the vast majority of women that disappear in Alaska are indigenous. And I went, okay, is that supposed to alarm me? The vast majority of people in Alaska, period, are indigenous. And so, yeah, probably. So I actually went and downloaded the data. Because you go out to Alaska and they have missing people data. It's all available. And I haven't I haven't actually done an analysis of the data, but I do have the data. All right, now that we have that in our calculator, I am going to once again draw a scatter plot. And I'm going to go to my second stat plot, second y equals. And I need to change, yours is probably okay. But my stat plot that's on is going to be still using the data from L1, L2. I put my data in L3 and L4. So I do need to change that. So I'm going to hit enter. And I'm going to change that to L3. So second 3. And I'm going to change that to L4, second 4. So just to make sure that my scatter plot is plotting the correct thing. Now I'm going to get out of here. And I'm going to go into my y equals, and I'm going to clear out all that stuff I got in there. Because I don't want it to graph. I don't want to graph it. All right. So now that I have my y equals cleared, and I have my stat plot going to graph my data, I'm going to go to the zoom button, which is smack dab in the middle at the top, and I'm going to do a zoom 9. And that's going to reset my window to fit my data. Oh, I got an invalid dimension. What have I got here? Second plot step 1. Did I actually not get that data in there? Oh my gosh, I'm going to be so mad if it disappeared. Sometimes when I have my calculator on and I put the data in, oh, it's an L4. No, where is it? It's gone. Dang it. I put this data in here yesterday. I promise you I did. Okay. So it's pressing. I know I did. I put it in my calculator yesterday. This is, ugh. All right, give me a second. I never even turned this computer off. I don't know why it cleared the data out. All right. Okay. So it gave me that error because it couldn't find data in L3. Whoops. Okay. Oops.
So how did you change that to L3 and L4 on your plot?
Go to stat plot and go down to where your X is, X, whatever it's called, and do second 3. And then go down to your Y values and put second 4. So does your graph look fairly linear?
Yeah. It's all jumbled up at the beginning and then it's separate.
It's because the years.
Yeah, they needed, they said no.
It's because they had that big jump in the number of years. Oops. So this is easy in some ways when you're doing it on a computer and hard in other ways. Because I got fat fingers. And this emulator I bought years ago, years and years and years ago. It was about $100, so it's about the same price as the calculator. You just can't put it in your backpack, carry it with you.
Why do I need to pay $170 for a calculator?
What was that?
I said, why do I have to spend $170 on a calculator? Lots of programming.
It's a pretty spiffy calculator. Okay, last one. I hope I inputted those correctly. For all the good it did me, put it in yesterday and then make sure it was right. All right, let me go back. So now I put it in L1, L2, so I got to go fix that. So let me get out of here. Let me go back to my stat plot. And I'm going to change it back to L1 and L2, since that's where I put it. So second one, second two. Okay, now I should be good to do a Zoom 9. Zoom 9. Is that what yours looks like? Okay, so what's the next thing we're going to do? We're going to find the regression equation that fits our data the best, and we're going to graph that along with our scatter plot. Now, it looks fairly linear, so we might as well go ahead and run a linear regression on it. So I'm going to go out of here. And I'm going to go back into my stat menu, right? Stat. And we're going to go over to calculate, correct? And we're going to calculate number 4, the linear regression. And again, I need to tell my calculator where I put my X values, my aligned years. I put that in L1. My Y values, my population, I put that in L2. I don't have a frequency list. So I'm going to go down here and I'm going to go ahead and store that regression equation in Y1 so I can graph it. So how do I find that? Do you remember? We go variables, Y variables, function, Y1. So now it's going to store that equation in my Y1. Okay. So now we're going to go down and we're going to calculate it. So again, to store it, variables, VARS, Y variables, which is the second one over to the right in the menu, function, which is number 1, and then Y1, which is number 1. Okay, so let's calculate that. So the line that fits my data the best has a slope of 2.6067 and a y-intercept of 177.195. So the equation of the line that fits my data the best is 2.607x plus 177.195. Okay, now when I hit the graph button, it's going to graph my scatter plot and my line. So that is my regression line. Does that look like a fairly decent fit? Fairly decent. And if you go back to your y equals, you can see your equation in your y equals 2.6067295436133x plus, let's just arrow over there, 177.194962229. It carries it out to 10 decimal places. All right. Part D of this problem states this. So we've done part A, B, and C. Let's look at D. If we align the data to represent the years after 1950, then X equals 10 corresponds to 1960. So when we put our data in our calculator, we align the data to be the years after 1960. So our X value started at 0. If it's after 1950, 1960 minus 1950 would be 10. So what we need to do to realign this data is change all of our L1s by 10. We need to add 10 to it. So do I want to go back in there and type 10, 15? No, I do not. So here's what I'm going to do. I can realign my data. So I'm going to go stat, edit, go back to my list, go to my L1 list. I can adjust that aligned data by 10 by just adding 10 to the list. And here's how you do it. So arrow up to where the L1 is highlighted. You see that? And down at the bottom, it says L1 equals whatever. I'm going to change that to L1 plus 10. So where's my L1 at? My L1 is above my 1. So I'm going to go second 1. So you see down at the bottom, it changed to L1. And I'm going to add 10. So it's going to take every single solitary one of those L1 values and add 10 to it. So when I hit enter, did you see it change? Well, that's kind of slick.
Oh,
It changed all my L1s and added 10 to them. Now, if you wanted to go back to the original aligned data, you could just go up there and subtract 10. And you'd go back to your original aligned data. So now, if I graph this again, I'm going to do a zoom 9. Now it's still graphing that original regression equation. So when I aligned it down, the Y values changed. So I need to run the regression. So I'm going to go stat, calc, number 4. And the data is still in L1 and L2, but I do need to restore the regression equation. So variables, Y variables, function, number 1, and then calculate again. So it changed it. Did it change it some, the B? Now when I hit the graph again, then you have the regression line that fits that data. Okay. I probably should have done this before I changed the model, but that's okay. I can do it. So in both of these, they say, let's just do one of them. Part F says, in both models, estimate the population. Oh. I guess they don't ask me to do that. I don't know where my brain was. Use both unrounded models to estimate the population in the year 2000 and in 2010. So you can use the model that you have to do these estimates. Now I'm going to real quick go back and I'm going to realign that model to the original. So to do that, I'm going to go stat, edit, and I'm going to take that 10 away. So I'm going to go second 1, L1 at the bottom, and I'm subtract 10. And I hit enter and it goes back to the original alignment. Now I got to go run the regression again. So I'm going to do stat, calc, 4, variables, Y variables, function, number 1. Calc. Graph. Okay, so there's the original regression. And it says, okay, then estimate the population in the year 2000. So the year 2000 would be what, 40 years after 1960, if you align the data? So what you want to find is the Y value given X is 40. So how do you do that? use your calc menu, which is above the trace. Do you see your calc menu? What is number one? Value. It calculates a Y value for a given X. So if you type in 40 for X, it will find the Y value, which is the population in the year 2000. So we hit enter. X is what? The year 2000 is 40 years since 1960. You type in 40, boom. So what's the population estimate? 281.46 million. Now, if you wanted to find it for, what was the next year we were going to find it for? 2010. So 2010 is what, 50 years after 1960, if we align the data. So again, how do we do that? We go second, calc, value, X is 50. Now, if you're trying to calculate, is that 307.5 million? If you're trying to calculate a value that's off your screen, it will throw an error. And so when it does that, you just change your window to make your window bigger. Now, I don't want to go through the whole rigmarole of changing the model back to the other aligned model, but it predicts the same value. The other aligned model does. All it does is it moves the X's and the Y's in the coordinate plane, but the value for a given X is going to be the same for either model. All right. Isn't this fun? Did you mean that sincerely? Most data from which the functions and applications are derived represent end-of-year totals, FYI. Thus, when modeling, we make the following convention, unless otherwise specified. A point on the input axis, the x-axis, indicating a time refers to the end of that time period. For instance, the point representing the year 1999 means at the end of 1999. Notice that this instance in time also represents the beginning of the year 2000. Right. Okay, so how do you turn on the goodness of fit measure? That R value that you saw on my screen measures how good a fit your data is to align. So for those of you that didn't see it when you ran the regression, this is how you turn it on. Okay, so you go to the mode. Do you see your mode button right next to your second button? And do you see down here the stat diagnostics, which is almost to the bottom here? Do you see how that is? See the stat diagnostics? Do y'all see that? You turn that on. So yours, if you didn't see it, yours is off. You go over, highlight the on, hit enter. That's the easiest way to turn it on. Okay, so now when you run your linear regression, and I'm not going to store it, I'm just going to run it. You should see an R squared, which is called the coefficient of determination, in case you're interested, and R. And R is called the correlation coefficient. And the correlation coefficient tells you how good a model your data is to a straight line. The closer R is to 1, the better your fit is to that regression. If it's positive, it is a positive regression. It's a slope that goes up. If it's negative, it's a line that goes down. So the sign of it doesn't matter 1 iota. The closer it is to 1 or -1, the better your fit is. So since we have an R of 0.997, that is pretty close to 1. This is a good fit. So that line right there, the 2.6067x, plus 177.195 is a good fit to my data. A very good fit, an excellent fit. If it's perfect, R would be 1 or -1. All right. I need to redo my pacing schedule. Let's see how far we can get. We're going to take a left turn. And we're going to talk about systems of linear equations. We're going to solve them graphically, which is the easiest way to do it. And then we'll solve them algebraically using substitution and elimination. Now, it's been my experience as an algebra teacher for nigh on 30-something years that you enjoy doing this. This is kind of a fun thing for students. You like to solve systems of equations. Then we'll use systems of equations to model a problem. The most common problem is cost and profit and revenue. And then we'll look at whether or not systems are inconsistent or dependent, which we talked about during the 10 o'clock period. Okay, what is a system of linear equations? A system of linear equations is a collection of linear equations containing the same set of variables. A solution to a system of equations in 2 variables is an ordered pair that satisfies both equations. So both equations are lines. Lines consist of an infinite number of ordered pairs. If the lines intersect, then there is an ordered pair that satisfies both lines. That ordered pair is the solution to that system of equations. So let's say you want to invest some money. And one account pays, I don't know, 5%. So you can invest in a CD that pays 5%. There's another bank that offers you maybe a shorter time frame, but it's going to decrease the amount of interest it pays. Because if you're going to draw your money out faster, then it's going to pay a smaller interest rate. Let's say it pays 3%. And let's say I have 10,000 bucks to invest. How do I figure out how much money I invest in both of them if I know how much interest I want to earn? So the reason this is a system of 2 equations and 2 variables is you have 2 different accounts. And you're investing 2 different amounts in those 2 accounts. So you have 2 variables. You have how much you're going to put in at 5% and how much you're going to put in at 3%. So you have 2 different variables you're trying to figure out. That makes this a system of equations. So if there are 2 different values you're trying to figure out, it's a system of linear equations. Break even. So we've talked about this. Profit is revenue minus cost, but there is a point where you break even. Your profit is 0. That's where your cost equals your revenue. Well, that's the intersection of your cost function and your revenue function. So the break-even point, if you're going to ever run a business, your break-even point is where revenue and cost intersect. Okay. Suppose a company has a total revenue for a product given by R equals 5,585x, 5,585x, and its total cost is given by a cost function, which is 61,740 plus 440x. Both of those functions, the revenue and the cost, both of those are linear because your x is being raised to the first power, correct? So those are both lines. Where x is the number of thousands of tons of the product that are produced and sold per year. The company is said to break even when the total revenue equals the total cost. That is when R equals C. Find the number of thousands of tons of the product that gives break even and how much the revenue and cost are at that level of production. So what I'm going to do is I'm going to graph this, because I'm going to graph the cost function, I'm going to graph the revenue function, and I'm going to see where they meet. Okay, so let's do that. Yeah, I know. I'm going to have to visit Amazon and replace this. Stop that. Okay, so I am going to, in my y equals, I'm going to graph 5,585x. Now, obviously, I'm going to have to do something to my window here. And in my y2, I'm going to graph 61,740 plus 440x. So I'm going to graph both of those. So I got to do a few things to my calculator. The first thing I need to do is go turn off that stat plot, because I don't want it graphing those scatter plot over the top of my y equals. So I'm going to do second stat plot, and I'm just going to turn it all off. I'm going to do number 4. Turn it all off. Okay, then I'm going to go to my y equals, and I'm going to clear out what I got in there, because that was the regression equation we calculated previously. All right, so the first thing I'm going to put in is my revenue equation, 5,585x. Okay, and then in the y2, I'm going to put the cost, which is 61,61740 plus, what was that plus? Oops, that's the wrong button. Plus 440x. Now, since that second equation, the y-intercept is 61,740. So the constant part of your linear equation is your y-intercept. Since that starts at 61,000, I'm probably going to have to change my window to like 70,000. So in the y direction, I'm going to go from 0 to 70,000. Now, it is appropriate that I start at 0 and go up, because I don't have a cost or revenue that's going to be below 0. No negative cost or revenue. And then the x values, I have no idea. So I might change my window from 0 to 100 and see what that looks like, and then adjust it accordingly. So before I graph this, I'm going to go to my window, and I'm going to change my x min from 1 to 0. And my x max, I'm going to change that to 100. And just so that it looks prettier and I don't get like 900 million tick marks on the bottom, I'm going to change that scale to 10. And then my y min, again, it's appropriate to start at 0. And I'm going to go to what, 70,000? Because my y-intercept is 61,000 something. And then I'm going to change that y scale. I'm going to change that to, I could change it to 1,000 or 5,000. I'm going to change it to 5,000 just because. Okay, and then we're going to hit the graph button. And I can see where they intersect, but my x is way too big. So I'm going to change and how to, I just tried something, right? And it's too big because it's intersecting way over here. I don't want all those x's up there. So I'm going to change my x window. I'm going to change that to 20 and maybe change the scale to 5. I don't know. This is fairly arbitrary, by the way. Let's see what the graph looks like. Oh, it looks a little bit better. I should have had my y window go up a little bit higher, but it's okay. It doesn't matter because I can see the intersection. And where those two lines intersect is the break-even point. Now, do you remember how to find an intersection? How do you find an intersection? So we're going to go second trace to the calc menu. And what's number 5? The intersection. And all you need to tell your calculator is the 2 lines and a guess. So it's blinking and it says first curve. And you see at the top, it's blinking on my revenue line. That's good. So I hit enter and it moves up to my cost function, correct? That's good. So I hit enter again and then it says, what guess do you want to guess? Oh, that's fine. Where I'm at's fine. So I hit enter a 3rd time. And what's the intersection of those 2 lines? When X is 12 and Y is 67,020. So the production level that causes me to break even is 12. And I think this is, what's our units again? Thousands of tons. So 12,000 tons of production, that's where I break even. So what's the revenue and the cost when I produce 12,000 tons of product? The revenue and cost both equal what? 67,020? And that that's just in dollars, right? Yes. Now, what happens at the break even? So the revenue line is the blue line. The red line in my graph, the red line is the cost function. So what happens when we produce more than 12,000 tons of product? Does our dot go above the break even? And do I start making a profit? So why is it important for us to figure out where we break even? Because we want to know, where do we start making a profit? There is a reason we do this, math crud. There's actually a reason. Okay, so how do we solve, in general, a system of equations? The first method that we learn to solve a system of equations is graphically. So how do we solve this system of equations? Now, I don't know what these 2 equations represent, if anything. I don't know. But can I solve that system graphically? And the answer is yes. And so what I'm looking for is the ordered pair XY that satisfies both of those equations. So there is, hopefully, an ordered pair that satisfies 3x minus 4y equals 21 and 2x plus 5y equals -9. Hopefully there's some ordered pair that satisfies both of them. So how do I find that graphically? Well, I have to graph it. And your calculator is kind of stern in its requirement for you to graph something. For you to be able to graph it, it has to be solved for y. That's the only way you can graph it. So in the previous problem, they told us that the revenue was something X and the cost was something plus something X, right? So they had both of those equations solved for us. Those are not. So what do I have to do? I have to solve them for y. So you take the first equation. The hardest part about solving these by graphically is solving for y. So we want to solve that for y. So I'm going to isolate the y on one side of the equation. What do I have to do? What's that? Subtract the 3x. Then what?
Divide the 18 by -1.
And that is what I'm going to put in my calculator right there. I'm not going to set the signs. We'll make a sign error. So that's what I'm going to put in my calculator for y1. 21 minus 3x in the numerator of a fraction divided by -4. Okay, let's solve the second one. What do we do? Subtract the 2x. Then what? Divide by 5. And that is what I'm going to put right there in my y2. Yes.
What if you actually do like the 21 minus 3 and the -9 minus 2x and like put it in the calculator like that?
That's
Like if you put 18x over -4, will it screw the,
well, I don't have an 18x. I have a 21 and a minus 3x.
so you don't actually do that?
So that's, they're not like terms.
Yeah, yeah, sorry, my bad.
Oh, no problem. No problem. Okay. Let's go. This is my last day of class for the week, so I will be able to replace this by next month. All right, so let's put that in. So the first thing I need to do is go clear out what I have in there. Okay, so I'm going to put that fraction 21 minus 3x over -4. So how do I find my fraction? Do you remember? Number 1, right? Now, those other 3 have purposes. We just don't use them very much. Okay, so what did I have? 21 minus 3x divided by -4. Okay, and let's put the next one in. What was that one?
-9.
So alpha y equals number 1. And you said -9 minus 2x, right? Over 5. Now, my window is all messed up, correct? Because I just graphed that revenue cost function. So I'm going to go back to a standard window. How do you get back to a standard window?
You go to Zoom.
Zoom 6. So go to your Zoom. Zoom 6 is your standard window. So can you see the intersection of those two lines? As long as you can see it, you can calculate it. Okay, so how do you calculate it? Do you remember? Well, start with your calculate menu. So where's that at? Above the trace? Does anything look familiar? No?
Interesting.
Intersect. You're trying to find where those two lines intersect. So are you going to do number 5? Because where they intersect is the ordered pair that satisfies both equations. That's the solution. The solution to a system of linear equations is the ordered pair that satisfies both equations. So intersection. First line is that 21 minus, okay, that's good. Hit enter. Second line is the -9 minus 2x over 5. That's good. That guess is fine. So where do they intersect? Where x is 3 and y is -3. So they intersect at the ordered pair 3, -3. X is 3, y is -3. Now you could probably trace over there and get pretty close, but why should you trace over there and have to hit the arrow and get over when you can just calculate the intersection? What's that? Oh, well, you do that. You do that. Yes, you do. As a matter of fact, you students have a tendency to do that. So we found x is 3 and y is -3. Is that correct? So the ordered pair that satisfies both of those equations is 3, -3. And you can check to make sure that works by plugging it back in, put 3 there and -3 right there. And I always do this in my head, 9 plus 12 is 21. Put the 3 right there and the -3 right there. That's 6 plus 15, what is that? That's a -3, that'll help. So that's 6 minus 15 is -9. I knew it had to be 3, -3, even before checking it on. So that's how you solve a system of equations graphically. And then in your slide deck, it has all the goody stuff there. And you can see they did a little bit of finagling with their equation. I didn't bother, doing any finagling. I didn't need to finagle it at all. It was fine. One of them, the second one, no, the first one, actually divided by the negative. Too much work. Okay. Now there are algebraic methods for solving systems of linear equations. Again, either you solve it graphically or you solve it algebraically. You are looking for the ordered pair that satisfies your two equations. That's what you're doing. So you're looking for an x value and a y value that will satisfy the two equations. So substitution. A second solution method for a system of linear equations is the substitution method, where one equation is solved for a variable, and that variable is replaced by the equivalent expression in the other equation. So you take, can you see who's looking in the door? Is he just standing there?
He's just talking, he's facing the other way.
Okay, thank you. That whole thing yesterday with the strangers got me kind of on edge. Okay, so what you do is you take one of your equations, and solve for one of your variables. Does it matter which one you solve for? Nope. And then you take that expression that you got for that variable and you plug it in the second equation. So it's substitution because that's what you're doing. You're substituting that expression into the other equation. All right, so we need a couple of definitions. So we're in a functions and modeling class. So we are looking at real life models. That's what we're trying to do anyway. So it might be a good idea to have some definition. Okay, what's the demand? The demand is the quantity of product that is demanded by consumers. And we'll talk about Apple products in just a minute. Supply is the quantity that's supplied. If you have a surplus, it's because your supply is bigger than your demand. So I have more Apple iPhones than people are demanding. If I have a shortfall, which is typically what Apple does, shortfall means that my demand is higher than what I actually have in stock. So my demand is greater than my surplus, so I have a shortfall. And what you want to work for is market equilibrium. You want your supply to be the same as your demand. They call that just in time. So I have the supply that's needed just in time for the demand. And that's what you want because you don't want a lot of supply sitting in inventory, not making you any money. So every time I pass like P&K or someplace, and they've got millions of dollars in inventory sitting out there in the lot, I go, holy cow. How did, obviously they're not paying for that. They're holding that property, John Deere owns it, and or Case owns it, or whoever, they actually own it. And when they sell it, they make a profit from selling that item. They're not actually carrying, $10 million in inventory. Because if you got, what's a combine these days? $250,000? Is it more than $250,000? Is it? So if you got 5 combines out there, my husband bought one for $3,000 and rebuilt it, a John Deere combine. Anyway, suppose that the daily demand for a product is given by P equals 200 minus 2Q. So that's the demand equation, where Q is the number of units demanded and P is the price of the unit. So P is price and Q is demand. And they use this across the board in every business class, everything. They use Q as the number of units and P as the price. And the daily supply is given by P equals 60 plus 5Q, where Q is the number of units supplied and P is the price in dollars. Market equilibrium occurs when the supply quantity equals the demand quantity. That's what you want. And when the prices are equal, that is, when Q and P both satisfy this system. If the price is $140, how many units are supplied and how many units are demanded? That's a simple substitution. Does this price give a surplus or shortfall of the product? What price gives market equilibrium? Okay. So the first question, part A, you simply want to find what's the supply and what's the demand if the price is $140. So my price is 140. And my demand equation is P equals 200 minus 2Q. So if we replace the P with 140, we can find how much is demanded. Okay, so what do we got? Subtract 200 from both sides. I'm going to do this real quick because I'm out of time. So we get Q is 30. So the demand, if the price is 140 bucks, the demand for this particular product is 30 units. Okay? So what's my supply equation? My supply equation is what? P equals 60 plus 5Q. Let's let P be $140. So if I charge 140 bucks for this stuff, what is my supply going to be? And of course, that actually does affect your supply and demand, your price, does it not? So if you lower the price of a product, maybe, typically the demand goes up. More people buy it because it's cheaper. If you buy a $1 million combine, what's the demand for a $1 million combine? Well, not a lot. Who's got $1 million to spend on a combine? So the demand goes down if the price goes up, those kind of things. That's typical. Plus 5Q. Subtract 60 from both sides. Divide by 5, and you get Q is 16. Okay, so my demand is 30, but my supply is 16. So are you supplying what's demanded? No. So do you have a surplus? No. Do you have a shortfall? Yes. So if you're not supplying what's demanded, there's a shortfall of product. Pardon?
Shortfall? Shortage? Isn't it also known as shortage?
Yes. Yes. Okay, so what would equilibrium be? Equilibrium would be where your supply equals your demand. So where does your demand equal your supply? Well, if this is demand and this is supply, do you set them equal to each other? And that you know how to solve. You know how to solve that, right? I would add the 2Q to both sides because I want to control the sign. Then I'm going to subtract the 60 from both sides. 140 equals 7Q, and then divide by 7. So 140 divided by 7, is that 20? So when your amount you supply and the amount you demand is 20 units, then you're in equilibrium. Your supply equals your demand, which is what you want. Because then you don't have products sitting in storage someplace costing you money. All right, are there any questions? I did not get through, I'm telling you, I'm gonna have to redo the pacing schedule. So obviously I can't make section 2.3 due Monday. So I'll push it out again. And next semester, they will benefit from you guys getting things pushed out. All right, any questions? All right, have a good rest of your week and we'll see you next Monday.
Have a good weekend.
Can you take it Monday?
Yeah.
Oh, be fine. Okay, I'm in class from 8 to 9:15. Are you gonna take it with me or are you gonna go to the testing center?
Probably a testing center.
Okay, then don't worry about it.
Oh, okay.
I'll just put it in the testing center and tell them you're gonna take it Monday. Okay? How's your homework coming? You asked me for an extension, but you didn't tell me how much you
I
wanted.
got it mixed up, so with the review and then, the regular class. I got like the late assignments done with the review, and then I went over to the actual class and I totally blanked, and I was like, oh. Scroll down. Like, past due. I'm like, oh, okay, so I need to get on, but I worked on that last night and I'm gonna, do some more tonight.
Okay, so I had them do like last Friday, I think.
Right, and I think I did, say my homework's done, it's just those quizzes.
Okay,
that
okay.
I'm
I
terrible
will,
at
I will
quizzes.
try to remember.
Even if it is just the 5 questions, the word quiz just.
Don't let it weird you out. So I'll go and extend those out till next Monday
Okay,
so that you can practice for your exam. Okay,
thank you.
you're welcome. Yes,
Is there any way you can use to this weekend to get my subscription?
you can get 2 weeks free.
How do you get 2 weeks free?
You got your computer with you?
Yes.
Pull it up.